nails. I'm going to teach you that. If you're going to put a grand piano on your deck to make sure the nails are closer together, are we clear? Okay, as I said, I learned quite a bit from consulting by calculating this to landscapers, and I got my depth with me. Okay, and it's useful stuff. Clear. So the next time, the first thing that you give your dad, you're going to tell a pal, you're going to buy a set of nails, and then we'll do experiment. What experiment we'll do? How much force to pull the what? Nail out. Are we clear? Then that will help you determine your what? The spacing. Not like, okay, son, every 5 palms, 1 nail. Every 5 palms, 1 nail. No. Okay. As engineers, we have to be more constructive than that. Okay. So now, so how do we do the experiment? I'm going to draw the schematics now. I'm going to draw the schematics out. So this is our nail. And this is a piece of wood. And this is our nail. To pull the nail out, you pull in this direction. So this is the resistance force. Let me put it as 1 nail. Okay, so that is your resistance force. Can someone tell me how is this related to shear flow or shearing stress? Anyone? Yes. Yes, there's a reaction force, but where's the reaction force acting on? If you pull out the nail, what surface are you hitting on? Vertical or horizontal surface, as you can see down there. So which part? Is it the head or the body? Good. Where the resistance is, so the nail wants to pull out this way, the resistance is doing what? This. We clear? So if I put an element down here, the element will now look like this. This is the resistance force or resistance stress. And if we look at shearing stress, we calculate shearing strength on which surface? We calculate on the what? On the vertical surface. Are we clear? So that is why when we determine the shear flow, we are still looking at what surface? The what? Vertical surface. Are we clear? This has to be very clear because the orientation is not the same. The orientation of the nail is running where? It's running in the horizontal direction. Why are we calculating the vertical phase? Exactly like how I explained to you why we consider the vertical phase when analyzing what? Shear failure. Are we clear? Right. Now, the next thing that I'd like to recall for you, okay, is in nails or in fastener, we have 2 things. Okay, we have single shear. Okay, and then we have double shear. Just to quickly recap with you, if I'm going to draw a single shear configuration, so for this case, the shear stress is equal to P over what? A. This is your A. Yes or no? I mean, this is where failure will occur. In double shear, draw the nail first. So these are the, and these have an extension, do apologize. And for double shear, failure will occur in these two regions. So for this case, the shear stress is equal to P divided by 2A. The 2A is because the distribution to twice the area. Are we clear? Okay. So now, you know there's single shear, there's double shear. If you look at this structure, single or double shear? Anyone? Yes. Double shear. Well done. Okay. So this is a classical case where you have what? Double shear when you have a shear force coming over here as what? As Vy. Okay. So now we got everything sorted out. Okay. We already know that failure will occur due to three reasons. Failure will occur due to bending moment. Failure will occur due to the shear stress, due to the, shearing stress due to the shear force, or failure can occur at the what? At the joint. Okay. So now let's do the first thing first. Okay. Let's focus on what we're going to do first is failure due to the fastener. Okay, we are going to determine failure due to the what? Fastener first. Okay, so the first thing we are going to do is we are going to determine Q. Q is equal to fastener resistance force, and then we're going to divide by the spacing. Okay, so this will be, so resistance force is 600 pounds. Divide by what? Divide by 6. And then we have to multiply a 2 over here. This 2 is because of double shear. Okay. So 600 multiplied by 2 divided by 6. So it's equal to 200 pound per inch. Okay. So I'm not going to find the second moment of area. So we are given that the IZZ is equal to 2902 inch to power of 4. Okay. So now the next thing that we are going to do is to find our, so the formula that we're going to use, we're going to find Q is equal to VQ over I. We know Q, small q, we know the shear flow, we know I, we don't know Q, we want to find what? V. V is what we want to find. Okay. So Q we would like to determine. So what will happen now is you have a Vy. We're going to apply the rule is that the member has to what? Distribute the what? The shear forces or the shear flow. Okay. So the area to consider is this top area. Over here, this is our centroid. And the rule still stand, the first moment of area cannot cross the what? Cannot cross the centroid. Okay. So from here, we are going to determine our Q. Okay, so Q is equal to our width multiplied by depth multiplied by y bar. Okay, so we will have our width. So width is 6. Our depth is 4. Our y bar is 5 plus 2. Okay, so this will be equal to 5 plus 2 times 6 times 4 is equal to 168 inch cube. Okay. So after finding this, we know that Q, so we know that Q is equal to VQ over I, and this will be equal to what? This will be equal to the value we calculated, which will be equal to 200. Okay, so this will be equal to 200. Okay. So if you look at over here at the top, right, how we draw, the shear flow will go to the, I'll sketch the shear flow on a different diagram. The shear flow will go to the left and will go to the what? Will go to the right. Okay, our shear flow will go to the left and go to the right. So from here, we need to find the relationship, or we need to find what is our V. Okay. So we know that Q is equal to VQ over I equal to 200. So V is what we don't know. I is 2902. 2902. Q is 168. And this is all equal to what? 200. Okay. So from here, your V or Vy, I'm going to change this to Vy. Okay, I do apologize. So Vy is equal to 200 multiplied by 2902 divided by what? Divided by 168. Okay, so 200 multiplied by 2902 divided by 168 is equal to 3454. Okay, it's equal to 3454. So on 3454 pounds. Now you have to be really, really careful down here. Okay, we just find Vy, and for this case, we have to note that Vy is not necessarily equal to what? Equal to P. Yes or no? Right? So we have to determine P. Before we determine P, we have to now construct the free body diagram. Okay. So now we go back here. Okay. We construct our free body diagram. So over here, we have a load. Okay, we have a beam. Over here is our P. And this is point A. This is point B. And we know that this is AY. And over here, this is what? BY. Okay. So the next thing that you can write, okay. So this is your X and this is your Y based on symmetrical loading